USGS, and she's going to be talking about these surface residual balls, or these tar balls, and how they move around in these nearshore environments.
Thank you.
Yeah, thank you.
So, my name is Soupy Dalyander. I work for the USGS in St. Petersburg. Anybody who caught the seminar a couple weeks ago, this is going to look familiar, so just try and find things you don't remember from before. But just to give you a little background, the part of USGS I work for is in the Coastal Marine Geology program, like I said. So what we study is what are the, how does sand move around on the beach, things like hurricanes impact the coastal areas. And so my background is actually in sediment transport. And all that means is how does sand or other objects move around in the beach. And so you'll see why, how we got involved based on that background. USGS, if you're not familiar with it, we're a federal science agency. We're actually prohibited by law from having any regulatory authority. We can't tell anyone to do anything. That's on purpose to keep the science from being influenced. We don't have a dog in the race, so a dog in the fight. So that's our role is to provide science that really informs managers, resource managers, natural hazards response, and so forth. That really benefits the public good, but we focus on the science end of it. And so I'm not going to go into too much detail on stuff that's already been covered, but sand and oil agglomerates is what we call them. So you hear these things called tar mats or tar balls. There's actually a reason I don't call them that. So when we were first brought in to look at this, I'm a scientist. What's the first thing I do? I go into Google Scholar. I do a lit review, right? I look up to see what do people already know about this. And I type in tar balls, and there's tons of publications. This is great. And so I look at them, and they're all about tar balls, literally balls of tar that float. And so all this wonderful research about how these things move around and what they do is useless to me because these things don't float that are left over from Deepwater Horizon. So in the surf zone, we've kind of heard oil and sand mix to form these dense agglomerates. So we call them SOAs. You can also, submerged oil mats are big ones. Surface residual balls are small ones. It's a size distinction, but they're all basically made of the same stuff. So these sand and oil mats, some of them could be tens of meters long or a couple centimeters thick. Smaller pieces can break off or they can form in situ, and they're a little bit more mobile. And that's what I'm going to be talking about. And so we've seen pictures like this now several times, so we'll dwell on that. You heard about the SCAT technique that goes out and assesses where oiling occurred. Coast Guard went out and removed material where possible, where it wasn't going to be ecologically worse to bring in the equipment to do so. But it kept coming back. And they wanted to know why. And so some of my thunder got stolen previously because we were brought in at the time of the spill, and not much was known about the dynamics. And now, thanks to research we've done, other folks have done, more is known about the dynamics. And so this question of why it kept coming back at the time prompted the Federal On-Scene Coordinator to charter the Operational Science Advisory Team, or OSAT. And that's where we, Coastal Marine Geology, were brought in because these, particularly the SRBs, like I said, I study sand and sediment, how stuff moves around, and they wanted to know how these things moved around. And so we were brought in to try and help inform response. Could we make response better? So the key questions that they had for us, where could mats still remain? If we find SRBs, does that mean there's a mat right there that we should go out and be looking for? Where is it all eventually going to go? And a big one, why do we keep finding these things in areas that we've already cleaned? Obviously, that's very frustrating. So the question of where could mats be hidden, and you heard a little bit about mention of the buried oil project. And so this was an attempt to identify where mats could still remain. And so the two pieces to that are, where could they have formed in the first place, right? That if you want to know where they still remain, you need to know where they started. The other question is, are there areas where they couldn't still remain because nature would have done the dirty work for us and broken the mats apart? So this first part was where we came in. Where could they have formed? And so in the case of sand and oil agglomerates, it's actually the sand that's the limiting factor. These things are 70+% sand, as you've seen. And so if you're out too deep, the oil mousse is at the surface, the sand is at the bottom. There's not sand and oil in contact to form this form of residual oil. That doesn't mean other things can't be going on out there, but in terms of this particular form of residual oil. We did some numerical modeling to look at where you actually would have enough sand in contact with oil in order to form these things. And you get it in the swash zone. This is sort of intuitive, right? You have the water and the oil on top of the water right in contact with the sand. You have a lot of energy. You have a lot of mixing. That's where you get some mat formation in SRBs. You can actually also get them under breaking waves. So when you have breaking wave conditions, you have a lot of sand being pulled up from the bottom. You have the oil mousse getting pulled down to deeper. It can mix, and so you can get this formation. But outside of the surf zone, you're not going to get them because, again, it's going to be sand limited. And so we didn't do the second part of it, but the second part was to say, all right, now we know where they could have formed. Where could they still remain? And that was done using aerial imagery and stereo-ortho-imagery. So they looked at, as you heard before, the beach was in an erosional state in most places when Deepwater Horizon happened. And so sand tended to come back. Anywhere where that happened and oil mats could have formed was a potential location to look for these things. And they actually found several by doing that, by looking in these locations where there had been accretion. On the flip side, if you have an area where you had oil deposited and now it's eroded, so the level of the bed is below where it was before, again, nature's done your dirty work. It's taken out the mat. They may have formed SRBs from it, but there's not going to be a big mat there because it's not, the surface where it was is now gone. So the second part of our work and the bulk of our work was related to these SRBs. And again, these are the questions that response was most concerned with. And we looked at this with a numerical model. Because as you've heard, it's very hard observationally to go out and find these things and see them. And so by using a numerical model and using our understanding of the dynamics of sand and similar materials, we could actually answer some of these questions. And so we built a numerical model. This models wind, waves, and currents. So when you're in the surf zone, when waves come in at an angle, they break, and they drive a longshore current that goes in one direction. And so this is the area that we modeled. You can see it covers from Alabama into the panhandle of Florida. There was another group that used the techniques we developed and applied it in Mississippi and Louisiana, but our model didn't extend that far to the west. And like I said, from this we know the wave conditions and the currents. One thing we did that was a little unique with this was, normally when people like me do this, we do what's called a time series run. So we say, all right, I care about what happened from September of 2010 to November of 2010. I look at the exact winds that happened then, and I'd run my model, and so my computer tells me what's going on. But that wasn't really what we wanted to do here, because number one, we wanted to know the future, and I can't tell you exactly what's going to happen in the future. And we also would have been very, we don't have a big enough computer, basically. The computational expense is too great to run the period of time we cared about. So instead what we did is we looked at scenarios. So we looked at all the wave conditions in the Gulf, and we looked at the different wave heights, wave directions, and we created a set of 80 scenarios that captured the variability. And so now the neat trick I can do is, in the past, I can take and at any given time I can match up what that time looks like in my scenarios and basically like build from these set of scenarios a time series. But I can also look in the future. I can look at what the average conditions are. What's the long-term, end conditions as far as what the currents look like, where the areas of current convergences are, things like that. All right, so now if my computer can tell me what the currents and the waves look like, what does that mean for the SRBs? And so SRBs, anything on the seafloor, moves when what's called the shear stress exceeds a critical value. All shear stress is that when you have liquid flowing over a surface, it gives a lifting force. And so how hard something is to move, it depends on how dense it is. Makes sense, right? How heavy it is. And how big it is. Bigger things are harder to move, denser things are harder to move. So by comparing what the model is saying the exerted stress is to what the critical values are for these SRBs, I can tell you when they're moving, and because of the currents, I can tell you the direction that they're heading. And so this was the classes we looked at. We looked at sand, just the sediment, natural sediment, and then we looked at 6 size classes of SRB ranging from a sand-sized little guy up to a 10-centimeter SRB. The other thing we looked at was integrated alongshore potential flux. This is a big phrase, right? All it means is that I can't tell you exactly where SRBs are going because I can't tell you exactly where they started. We know it covered a large extent of Florida to Louisiana, but I can't tell you where one particular one started, so I can't track it through my model exactly where it went. But what I can tell you is, and this makes sense, right, very basic, if currents are going this way in one location and currents are going this way in the other location, here's a good place to look. Similarly, in the middle where those two converge. Similarly, if you have flow going in one direction and that's starting to slow down, that's another area where this decelerating flow, that would be an area you'd expect to see these things. And so those were areas that we were looking for. So these are some of our results. This is, you're going to see a few of these plots. So all this is the ratio of the exerted stress, the force that's going on these things, to the critical value to move them. So if this number is bigger than 1, stuff's moving. If it's less than 1, stuff's not moving. If it's greater than 1, it's going to be in a really hot pink color, so that it's really easy to see. These are under the small wave conditions that are common in the Gulf of Mexico. This is for natural sand sediment going up to 2.5 centimeter SRBs and 10 centimeter SRBs. And what you can see, it's really easy to see, is that under these small wave conditions, the big SRBs aren't moving anywhere. Similarly for the 2.5 centimeter SRBs. Sand, on the other hand, can move in the surf zone. This is intuitive. You go out to the beach, you see sand moving around even when the waves are little. So sand is more mobile than SRBs, and that's actually important. Like I said, some of this is now known, but at the time, they weren't sure how immobile these things were. And so there wasn't a lot of understanding that these smaller pieces could be buried and exhumed, that they could be buried and unburied with shifting sand. But because they are less mobile than sand under normal conditions, small wave conditions, that's a process that's going on. What about big waves, storm waves? And this doesn't necessarily need to be a hurricane or a tropical storm. This could be a winter storm front that comes through. Well, sand is moving everywhere on the shelf, and this is consistent. This is something that's well known. If the model didn't say this, this would be a problem. It's moving out along the shelf. But now you're starting to see some movement of the SRBs, 2.5 centimeters in the surf zone, and it's hard to see at the scale, but even the 10 centimeters in the surf zone can move. And so during storm events, what can happen is these larger SRBs can start to move a little bit along shore. But then under smaller wave conditions, the sand is moving and the SRBs aren't, so that's when you can get a lot of this burial and unburial. So again, this is the results of our study, that they're not mobilized during low energy wave conditions, but they are mobilized under storm conditions. And this actually explains something that the Coast Guard had seen, and then they couldn't quite explain, was that when they go out after a storm, they wouldn't collect a lot of these things, which is counterintuitive, right? Everybody assumes that after the storm, these things break up and they'll show up. And so they kept saying, why are we not finding these? And what it is that during a storm event, you have a lot of sand come up in suspension. You have these larger SRBs, they start to move around a bit. Now the conditions start to die down, and the sand's falling out of suspension and covering them with a light amount of material. So you go out there and look, you don't see them. But over time, and this takes maybe about a week, the sand starts to get brushed off the top of the SRBs because the sand is moving and the SRBs aren't, and you find a ton. So you get a spike about a week later. And so when they go out and they'd find these things, and they'd say, we found a bunch of these things, and there wasn't a storm. You say, was there a storm a week ago? Yes. So that's a mechanism by which these things can explain some of what they were seeing. Again, we looked at potential flux, which this is just looking at what is the general directions of flows or fluxes of these things, so we can find areas. I can't tell you the exact amount, but I can tell you spatially where they're more likely to accumulate. And so again, where you have a convergence of flow is an area where you're more likely to have them, or if you have a deceleration where stuff is slowing down, stuff's going to be tending to start to stop moving and fall out of the suspension sand. So these are some results. This is Mobile Bay, so Alabama into Florida, and this is for 2 different wave conditions. So the white arrow shows the direction of the incident waves. So at the top panel, this is waves coming in fairly oblique to the coast. The dots along the coast, if they're green, it's eastward flow. If they're red, it's westward flow. And you can see that when the waves are coming in from this angle, you've got westward flow pretty much all along the coast. And that's the dominant direction of sediment transport, longshore sediment transport in the northern Gulf. So if you average everything, this is mostly what it looks like in most places. But under some conditions, if the waves start to come in a little bit more shore normal, you can have a much more complicated pattern. And so you can see, so here we've got westward flow, you've got this complicated pattern. So for example, here right near us, you've got, where we are now, you've got this flow to the west, flow to the east on either side of Pensacola Pass, indicates a convergence at Pensacola Pass. And this was actually an area that we persistently saw. So under many wave conditions, this was something an area that showed this. Whereas other areas, again, you can see convergences and divergences, but it depends on the particular wave conditions. We looked at inlets. So this is Little Lagoon Inlet. So this is Mobile Bay, it's on the coast of Alabama. It's a small inlet. And again, this is one of these plots where it's pink, it means stuff is moving, and when it's not pink, it means stuff is not moving. And this is for a 2.5 centimeter SRB. And so what you can see on flood tide is you have a pathway all the way through the channel where these things are mobilized. So as they're moving along, they can get into the inlets. But on ebb tide, there's flow asymmetry. The flow looks different on the ebb than on the flood. And you actually have a gap now where they're not mobilized. Well, if something can get in and it can't get out, you've just made a trap. So inlets can serve as traps for SRBs. And we see this, we looked at several different inlets. And again, because of the way flow patterns tend to be flood to ebb, inlets make pretty efficient traps for SRBs. So this is a summary of the numerical model results. The greater mobility of sand than SRB makes burial and exhumation likely. Like I said, you've heard other people say that at the time. This was something that wasn't necessarily well known or wasn't known at all because most of the work that looked at tar balls had looked at these floating things, which move in an entirely different way. Larger SRBs are unlikely to move along shore outside of storm events, but under storm events they can start to move. We generated these long-term distribution patterns. So we looked at what the patterns were over time. But basically, the bottom line is it would take a long time to reach that distribution pattern because, as I said, it depends on the wave conditions. And these things, because they get buried and unburied, when they're buried, they're not moving around. So it extends the time scale over which they could be found. And it also prohibits them from eventually reaching this long-term distribution pattern because when they are uncovered, they're going to move by whatever the wave conditions happen to be at that time. They also tend to be picked up or collected. Lastly, the inlet serve as traps for SRBs, and so that's an area that would be expected to be an area that you find more over time because of that mechanism. So we took all our results, put it in GIS format so that it was accessible to the managers looking at this and the responders looking at this. And so this is our website that has all of that. All of our data is online as far as wave heights and currents. It's been used actually to look at some other things related to the oil spill. And the methodology itself can be applied anywhere. So obviously the scale of Deepwater Horizon was unique, but in talking to folks since then and talking with, for example, Regional Response Team out in California, they see this form of residual oil in other places. And again, this gets back to this terminology thing that sounds kind of silly, calling them tar balls versus not, but they didn't realize it was something different. And they didn't realize that you couldn't necessarily treat it the same way and that these things were coming buried and unburied because they're dense. And so that's the only reason to be fussy about what they're called, is to make sure that everybody knows what they're actually dealing with. So should you believe what I just told you? No, of course you shouldn't. It just came off my computer. I could have made it up. But because I'm a scientist, I will assess my model and I will tell you how well it's doing. So we did a model assessment or model validation. We didn't cheat. In fact, we couldn't cheat. The Coast Guard didn't give us their data until after we'd given them our results. So we didn't tune the model. Starting in June of 2011, the Coast Guard collected some data about what they had collected in terms of the pound and the shape. This is not scat data, actually. This is collection data. So it was actually what was picked up. And like so they kept track of the amount, some basic information on shape. And they did this for SRBs and for map material. They spatially delineated it in a longshore segments, about 250 meters. This data was invaluable. I can't emphasize enough. Obviously, it was not collected for scientific purposes, but having this and then being able to do this and not, didn't really impede what they were doing was really, really helpful for us being able to look at what we were doing. So there's some limits because it wasn't a scientific data set, but it was really, really valuable. And so I'll just show you one plot of that. So this is the longshore variability going from west to east of the total mass of SRBs that were collected as of, I think this was 2013. You'll see the dashes are the inlets because of that trapping mechanism I mentioned, and because in between the inlets are, you hear from Joel, they're isolated systems. You don't expect them to cross. And so when you look into each of these, what are called littoral cells between the inlets, in most cases, you see a gradual increase. This is over the course of this is 2 years worth of data going from east to west, which is consistent with the patterns that we were predicting. So like I said, the dominant direction of a longshore transport is to the west here. You can also see the triangles are around collection points that were in inlets. And you can see that, like the model predicted, you get increased collection, particularly at Pensacola Pass, which, like I said, was an area that had these persistent convergences. Little Lagoon, Mobile Bay. Oops, Perdido Pass didn't match. That really bugged us for a while because that was inconsistent. Something was wrong. But what's going on there is that Perdido Pass has 2 jetties that extend out from the front. They also closed this off with a novel booming system during the spill. So not as much oil got in, surface oil got into the pass. And SRBs can't bypass these jetties. So you can't serve as a trap as though nothing gets in there in the first place. And so that's what explains this lower collection there. What we're doing now, so one of the things that we learned in responding to this is that a lot of what we have, a lot of the tools in our toolbox were developed for sand, and they weren't necessarily developed for these larger objects like SRBs. And we've done some work. We wanted to make sure, number one, how good are we doing with these tools, and how can we make these tools better? And so that's what we're working on now. We obviously don't want to put real sand and oil agglomerates out, because for a very obvious reason. So we're making artificial ones out of paraffin wax and sand. We make them in different sizes and shapes, and really get into, we deploy them in the surf zone, and really get into nailing down the formulations and the science behind this so that we're better prepared next time. So for example, one thing that I didn't talk about was cross-shore transport, final deposition, and that's because we didn't feel confident on what we knew and being able to predict that, but we'd like to be able to next time. And so that's what we're working on. We also took these to a lab, so because it's really hard to see things in the surf zone. This slide doesn't actually have the picture that this camera took, but you can imagine when you look underwater what it looks like. And we have some neat image processing tricks to try and find them. That's why they're so brightly colored, but they're still pretty hard to see. Whereas if we take them into a tank, it's relatively easy to see. And so what you can see, so this is looking into the side of a tank in a laboratory, the Naval Research Lab, and you can see these are sand waves moving and burying them. This was something that we hadn't really thought about, that in the tank it looks like is an important process. You know, when you think of barrow, you might think about like scour forming around the edge and them being buried by a light layer of sand. They can also get swamped by features moving over them, and that's where you can get, like Scott was saying, a meter of sand on top. You know, this is just a small sand ripple moving over, but it's going to bury it in a few inches of sand. And what if that was a sandbar that moved over it? You'd have a large amount of sand on top. We looked at the exhumation of them with this, and so this data is still being analyzed to improve these formulations. We also one area that we identified that was really hard to understand what's going on was the swash zone, because you've got water, you've got water bore coming up and hitting them, you have pressure gradients, and so that's another area we're trying to improve our model. So our conclusions, the work we did for the buried oil project was to identify the offshore extent of possible mat formations, so that by identifying where these things could have formed, they could look at changes in the bathymetry, changes in the topography, and identify where they might still be to focus where to look. The greater mobility of sand than SRBs makes this burial and exhumation likely. The larger SRBs are unlikely to move in storm events, but they're unlikely to move under lower wave energy conditions, but they can move around during storm events. We predicted these long-term distribution patterns, but because of burial and exhumation, this is going to take a long time to reach that pattern, if in fact it ever does, because of, again, once they get unburied, people start to collect them and so forth. Inlets serve as traps for SRBs, so finding a bunch of SRBs in an inlet is not necessarily indicative of a mat located there. And then we validated our results against this Coast Guard collection data. And so, again, I think this presentation will be shared, so these will be hot linked, and these are the USGS and public journal articles that have more details on all of this stuff. Thank you.
Okay, so now the long-awaited question and answer period. So if we can have our 3 speakers from this morning come on up. I'm going to ask you guys to kind of sit close to one